Okay, now let us discuss the next problem. So this says, so there is a compound something like this. Again, this problem is from aldehyde ketone. So this is from aldehyde ketone. This says CH3CO, and then we have CH2, and then we have COCH3. If this molecule is treated with NH2NH2, if you remember, NH2NH2 is also called hydrazine, NH2NH2 in acidic medium, this compounds gives something like this. There is a CH3, there is a CH3, double bond you have. Here you have a double bond, here you have a nitrogen, and here also you have a nitrogen, and then you have a hydrogen. So you are getting this kind of compound. Now problem says account for the formation of 3,5-dimethyl-pyrazole. So this molecule, so 3,5-dimethyl-pyrazole from hydrazine and 2,4-pentadione. So this is 2,4-2,3,4,5 pentadione. So dione, so 2,4-pentadione. So you have to account mechanism. Now the things is very simple. You know, the first step is H2O, it will be removed, and then if you remove H2O from here, you will get this kind of compound. So you have to remove 2 mole of water. That is very simple. Now you can write the mechanism of the same problem in acidic medium. So let me write mechanism. So if I write something like this, so we have CO. Are you able to get or not? Okay. So this is CH3. Here I have CH2, and then you have CH3. If I have acidic medium, I can protonate this one, and I will have plus. I am assuming that you can understand this step. So this is a first step, that is protonation step. And then now next step, NH2 can attack. So there is a lone pair. This lone pair basically can attack here. If it attacks here, this goes here. So you will have something like this. CH3, CO, CH2, COH, and then CH3. Now you have NH2, NH2. Now this nitrogen will have a plus charge because nitrogen getting 4. So now you have to remove H plus from here. So if you remove H plus, you will have CH3, CO, CH2. This mechanism is so simple. OH, NH. Now you have, if you remove H plus from here, you will have NH double bond, NH single bond, NH2. Now in the next step, if you protonate this H2O, let us write here itself, and you make OH2 plus, and you remove 1 H plus from here. I am assuming that you are able to understand these things. These things are done in the lecture. So these videos are basically supplement to the lecture. This is not a separate. If you cannot ignore the lecture, you have to have. So this is CH3, and then you will have double bond N, and then you will have NH2, and here you will have CH3. Now if you do the same step one more time, so what you have done? You have removed 2 hydrogen from here, and 2 hydrogen from here, and 1 O from here. H2O you have removed, and you have made this kind of bond. If you do the same thing from oxygen and 2, you will get something like this. If you remove CH3, so you will get CH3. Here you will have C, then you will have CH2, you will have CCH3, double bond N, and then you will have one more double bond here. So you will get something of this kind of compound. Now you see this compound and the initial compound, you are getting 1, 2, 3, 4, 5 membered ring, and 2 CH3 in the chain, in the branch. Now you see the original compound. You are having same thing, but only difference is now there is double bond between carbon-carbon and one double bond between carbon-nitrogen. Now here you see there is one double bond between carbon-nitrogen, one double bond is between carbon-carbon. You need one double bond between carbon-carbon. That is not there. So what we can do is we can write this molecule. So let us write N double bond C, and here I am writing C hydrogen, C CH3, nitrogen is here, and then double bond is here. Now there is a CH3 here also. Now in acidic medium, now we can do ketoenol tautomerization. So this is tautomerization. If I remove this hydrogen is acidic hydrogen, and put it here, this is a tautomerization step. Now if I do something like this, I will have CCH3 double bond N H CH, and then I will have a double bond CH3 C. Now why I am doing this? This is because now you see the benefit of doing this tautomerization. Now this step will be more stable because now this one lone pair, this lone pair, this double bond and this double bond. So 2 pi electron, one lone pair, there is a pi electron, this 2. So this compound will have 6 pi electron. And once this compound will have 6 pi electron, this becomes aromatic. And basically from this step to this step, so this step to this step, aromaticity is the driving force. So you are having only one lone pair. So let us put something like this to not be confused. So from this step to this step, we are coming because of this aromaticity. So in this step, aromaticity is the driving force. So you see, aromaticity is the driving force. Aromaticity is driving force for this reaction. Now this reaction is basically intramolecular reaction. First step is intermolecular. You are having this molecule, and you are having NH2. So you are making something like this. This step is intermolecular. One molecule, another one. Now this from here to here, this is intramolecular. So you can say this is intra. And this step is inter. So first step that is happening. So this is inter. So two steps, one is intermolecular, another is intramolecular. You can once again, are you able to understand or not? So these things are easy because I am removing H2O from NH2 and ketone only. So 2H2O is removed in the whole process, and we are getting the final product, and final product is basically driven by aromaticity. That is the important part you have to remember. Now this is a tautomerization step. That is also important. Now this tautomerizer will be more stable, this is less stable. So this is a major tautomer, this is a minor, because these tautomers are in equilibrium. This is a major, this is a minor. Okay, we'll discuss the next problem.